Bismillahirrahmanirrahim. Today, the topic we are going to discuss, or the chapter we are starting with, is the benzene and its compounds. This is the chapter 25. So, in this chapter, we are going to discuss about benzene and the compounds that are related to benzene. So, first of all, we will discuss what is benzene and how we can relate the ring of benzene and what are the bonds that are inside the ring. So, the benzene is made up of a hexagonal ring, which means it contains 6 carbons. That's why we say that it has a ring which is a hexagon made up of 6 carbons: C1, C2, C3, C4, C5 and C6. So a benzene ring is a hexagon made up of 6 carbons. 6 carbon atoms are bonded together in a particular way. So benzene rings, they are found in many compounds that are commercially important. And for those compounds, like the pharmaceutical ones, the compounds that are made synthetically in the lab or in industrial scale, they all contain benzene in their structures, or most of them contain benzene. So, the commercially important benzene rings, the benzene rings that are found in many compounds that have the commercial importance, are, for example, medicines, or we can say pharmaceutical compounds. The dyes and the plastics. So the organic compound, as you all know, are the compounds that contain carbon and hydrogen as their main units. So for the organic compounds containing one or more benzene rings, like benzene, they are also the hydrocarbons, like they also contain carbon and hydrogen that are the main constituent of the benzene ring. So this benzene is also one of the hydrocarbon, and that's why we are saying that the organic compounds that contain one or more benzene ring, they are called arenes. So in general, compounds of benzene they are known as aryl compounds, or we can say them the aromatic compounds. For example, we have the chlorobenzene. It has the chlorine as well as benzene. Benzene having attached chlorine on it is known as the chlorobenzene, and this chlorobenzene is one of the aromatic compound. Like we said that the compounds of benzene, they are known as aryl compounds, and this is one of the compound of benzene. And this is the halogenerenes, or we can say them as it contains halogen at the top of the benzene ring, so we can have the name of this compound as halogenoarene. So for the definition of arene, we can say that the hydrocarbons containing one or more benzene rings. So we have different theories for the structure of benzene, like we said that benzene has a hexagonal ring. And inside the ring, the bonds are present. Those are the alternate doubles and single bonds. Double, single, double, single. These are the alternate doubles and single bonds. So, to elaborate the structure of benzene, the scientist whose name was Kakul, he has given two of the structures, and those were considered as the Kakul's structures. So, according to this Kakul's structure, the hexagonal ring, this hexagonal ring, it contains three double bonds, and three single bonds. So, in journal, his structure mentions that the hexagonal ring contained three double bonds. So the chemist, and he also has given the two alternates, like this bond can be at this state, like two of the alternate benzene structures can be formed, and these were the Kakul structures, with which discuss that the benzene ring contains three double bonds. Three double bonds. But this was about the structure of benzene. Again, the chemists developed different analytical techniques. Chemists, they developed different analytical techniques, and they found out that benzene molecule has a planar structure. And the molecule is perfectly symmetrical. So this Cockle structure suggests that the three double bonds that are present inside the ring, these bonds are shorter. So the Cockle structure suggests that three of the double bonds, three shorter double bonds, and the single bonds, they are of longer bond length. So we can say that Cockle's structure suggested that three double bonds, CC double bonds, and three longer CC single bonds are present inside the benzene ring. And due to this, it produced the distorted hexagonal shape. See, double bonds are shorter and 3 single bonds, they are longer and they are producing the distorted hexagonal shape. So we cannot say that this hexagonal geometry is perfect hexagonal arrangement of carbon atoms in the benzene molecule. Actually, we were considering that this hexagonal arrangement is perfect and aligned. However, Kokul suggested that it is distorted hexagonal shape. So we can represent the benzene skeletal formula as this way. So this is the skeletal formula of benzene. So we can actually measure, or we can now measure the actual bond length. We can now measure the actual bond lengths of the carbon atoms that are present inside this hexagonal structure. However, this was impossible in 19th century when Kekulé worked on the benzene ring. So the carbon-carbon bond lengths that were the bond lengths of the carbon atom in the benzene, uh, they they are they lies between the values for CC single bond and CC double bond. As for CC single bond, we have the value of 0.154 nanometer, and for double bond, actually we have the values of 0.134. But in carbon to carbon bond length in benzene, they are 0.139, which means that they lies between these two values. If we discuss, or we go towards the depth of the benzene structures which were given by Kakul, then the chemistry of benzene suggested that the Kakul structure is incorrect, as if there were 3 double bonds in benzene, then it will undergo addition. Like the 3C double bonds that are present inside the benzene ring, they will undergo the addition reactions. Like if there are C double bond C, 3C double bond C in benzene, if there were 3C double bond C in benzene, then it will undergo addition reactions. In the same way as alkenes. However, this is not the case. For example, ethene, it will decolorize bromine water on mixing at room temperature. Ethene will decolorize bromine water on mixing at room temperature. But the benzene benzene needs the harsher conditions. So the actual structure of benzene can be explained by considering the bonding in molecule. The actual structure in benzene can be considered by considering the bonding in molecule. So each of the six carbon atoms in the hexagonal ring, they are sp2 hybridized. So when we are seeing these six carbons in the hexagonal ring, and we are saying that each carbon is sp2 hybridized, so this can be elaborated as the one pair of electron, like this carbon, which is sp2 hybridized, and if we see the electronic configuration of this, then it comes to be 2p2, and it can be as 2s1 2p1 2py1 and 2pz1 in its excited state. So this is sp2 hybridization, 1s and 2p's. So this one pair of electron is sharing the electron with one of its neighboring carbon atom. And again, this carbon is pairing with another carbon atom with the other electron. And this third electron is pairing up with hydrogen. So one with this neighboring carbon, one with this neighboring carbon, as there are three electrons which are forming sp2 hybrid shells. So these three electrons, they are combining in a way that the carbon, one pair of the electron with one of its neighboring carbon atoms, then one pair of electrons with its other neighboring carbon atoms, and one pair of electrons with a hydrogen atom. And these three are forming the sigma bonds. So three sigma bonds are formed. These are three sigma bonds. So each carbon atom with sp2 hybridized atomic orbitals form three sigma bonds. Each carbon in benzene with sp2 hybridized orbital is forming three sigma bonds. So that leaves one electron pair. This one electron is now left for each carbon atom. So this one electrons pair on each of the six carbon atoms in benzene. So each carbon contributes its one spare electron to a pi bond, and hence six pi bonds are formed. So these pi bonds that are formed in benzene, they are not same as the pi bonds in pi bonds in alkene. This is alkene, not alkene. Like pi bond forms in alkene. So these 6 pi bonds that are formed in the benzene ring, they are not same as the pi bonds in alkene. C double bond, C bond. So in alkene, the pi bond, helps to bond one pair of carbon atom to each other. Like one is the sigma bond, another is the pi bond, and this pi bond is helping both carbons to bond with each other. But in benzene, this is the case for alkene, but for benzene, each carbon contributes. So in alkene, a pi bond helps to bond one pair of carbon atom to the other. But in benzene, the 6 pair p electrons, these are actually pz electrons. So these 6 spare p orbital electrons, they are spread over all the 6 carbons. They are spread over all the 6 carbons in a hexagonal ring. And the 6 electrons in the pi bond, they are said to be delocalized. So the pi bonding in benzene is formed by the overlap of carbon p atomic orbitals. Okay, the pi bonding in benzene is formed by the overlap of p atomic orbitals. Like one pz electron from each carbon. So to achieve maximum overlap, this benzene molecule, it must be planar. And the lobes of p orbitals, they overlap to form the ring of delocalized electrons. Like these are the p orbitals. Those are the spare p orbital electrons, and these lobes of the p orbitals, they overlap to form a ring of delocalized electrons. Above and below the plane of carbon atoms in the benzene molecule. This is how this ring forms inside the benzene ring, which is actually the 6 delocalized electrons that are spread over the whole ring. This was all about the introduction of benzene ring, or the discussion about the benzene ring. Thank you.